Pluto, a distant and enigmatic smaller celestial body, was once part of our planetary family, but has recently been thrust into the spotlight due to alarming declarations made by renowned astrophysicists Neil deGrasse Tyson and Michio Kaku. They suggest that this icy world might be on a potential collision course with Neptune. But how could this happen, and what could be the consequences of such a massive event? Are we witnessing a rare galactic phenomenon, or is there more to this looming cosmic impact? Join us as we delve into the possibilities of a Pluto-Neptune collision. Pluto, once considered a planet before being reclassified as a dwarf planet due to its unique orbit, continues to intrigue and captivate the astronomical community. According to recent predictions by leading scientists, Pluto's orbit dangerously approaches Neptune's, leading experts like Neil deGrasse Tyson and Michio Kaku to raise warnings of a potential catastrophic impact between these two bodies, one that could pose a significant threat to Earth. But how could such an event even occur? Pluto's orbit around the Sun is unlike any other planet in our solar system. It takes an astonishing 248 years to complete a single revolution, meaning since its discovery in 1930, it hasn't even made one full orbit yet. But Pluto's fascination doesn't end there. Its orbit is marked by its highly elliptical path, diverging significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unique is its tilt of 17 degrees relative to the ecliptic plane. Its path is much more inclined compared to the other planets, adding layers of complexity to its orbital pattern. One of the most interesting aspects of Pluto's orbit is how it intersects with Neptune's. For about 20 years in each revolution, Pluto actually comes closer to the Sun than Neptune, contrary to what one might expect based on their positions in the solar system. This raises the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influence of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers struggled to grasp its unique trajectory, which deviated from the other planets whose orbits lie mostly close to the ecliptic plane. Pluto's orbit stood out due to its steep inclination and elliptical shape. The mystery deepened once astronomers realized that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit, despite these complexities, is proof of the intricacies of space mechanics. The three-body problem in space involves understanding how three celestial objects, like Pluto, Neptune, and the Sun, move and interact with each other through gravity. It's akin to trying to predict their future positions based on their starting points and gravitational pulls. In Pluto's case, this problem demonstrates how Neptune's orbit, along with the Sun's gravity, all interact in a complex way. Terms like Oth libration and scope libration, along with the VZK oscillation, are crucial to this puzzle. According to astrophysicists, what keeps all planets in their orbits is the concept of libration. In the context of Pluto and Neptune, this term indicates that whenever Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial division is critical in preventing their orbits from colliding. Scope libration, on the other hand, refers to the upward movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned largely above their orbital plane, providing an additional layer of protection from potential collisions. Another key factor in this equation is the VZK oscillation, named after the three scientists von Zeipel, Chi, and L.V., who studied how objects move in space. It explains how gravitational pulls influence their movements. For Pluto, this oscillation helps us understand why its orbit around the Sun is so unique. Although Pluto's orbit may seem chaotic, these oscillations help keep it moving smoothly over long periods. Recent computer simulations have allowed us to understand how the large planets, like Neptune, Jupiter, and Saturn, affect Pluto's orbit around the Sun. Neptune has a unique interaction with Pluto, where for every 2 orbits Pluto makes around the Sun, Neptune completes 3. This relationship helps stabilize Pluto's orbit. But Neptune isn't the only planet playing a role. Jupiter's gravity also plays a significant part in protecting Pluto's orbit, as does Saturn's. These tests show that Jupiter's gravity alone is strong enough to ensure Pluto stays on a steady path for a very long time, potentially billions of years. In essence, It's as if Neptune, Jupiter, and Saturn are all working together to ensure Pluto moves safely in space without running into trouble. These phenomena are essential to maintaining the order and stability of celestial bodies. Without these mechanisms, our solar system would be a place of much greater confusion and chaos. Celestial bodies like Pluto could easily collide with others or be ejected from their stable orbits, leading to a domino effect on other celestial bodies. For Pluto, particularly, discussions about it potentially colliding with Neptune remain speculative, thanks to the various gravitational interactions that keep its orbit stable. The three-body problem helps us understand how these factors shift based on how these objects pull on one another. Studying this helps us learn more about Pluto, our neighboring planets, distant galaxies, and their stars. Through mathematical simulations in the late 1980s, scientists revealed that despite these stable properties, Pluto's orbit is indeed chaotic. Minor variations in initial conditions can lead to significant changes over thousands of years. However, these unique properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively keeping the chaos in check. Recent computer simulations have helped us understand how the larger planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Neptune has a unique relationship with Pluto, where for every 2 orbits Pluto makes around the Sun, Neptune completes 3. This relationship helps stabilize Pluto's orbit. But Neptune isn't the only planet playing a role. Jupiter's gravity also plays a significant part in protecting Pluto's orbit, as does Saturn. These tests show that Jupiter's gravity alone is strong enough to ensure Pluto stays on a steady path for a very long time, potentially billions of years. So, it's as though Neptune, Jupiter, and Saturn are all working together. The concept of future comprehension in celestial dynamics holds significant importance, giving us a clearer understanding of the dynamic nature of planetary groups. The example of Pluto illustrates how even seemingly unstable orbits can achieve a state of balance through complex interactions of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and investigation to better grasp our place in the universe. Exploring the depths of space often leads us to confront the unpredictable nature of celestial bodies, and Pluto's orbit serves as an excellent example of this variability. The idea of orbital chaos, which refers to how slightly altered initial conditions can significantly affect a celestial body's orbit, is clearly represented in Pluto's case. This means that even small variations in Pluto's position or speed can drastically change its long-term orbit. Using advanced simulations has been extremely helpful for scientists in understanding Pluto's movements in space. These simulations employ complex mathematics to model how Pluto, along with other celestial bodies like Neptune, interact with one another. By adjusting small details in these simulations, astronomers can observe how even minor changes can lead to major differences in Pluto's path. In the late 1980s, these simulations revealed something quite intriguing about Pluto's orbit. Although factors like latitude and longitude librations help stabilize its path, its orbit can still be quite erratic. If starting with even a slight difference in where Pluto is or how fast it's moving, its path can appear significantly altered over time. However, even with this apparent instability, Pluto's orbit remains stable for long periods, like billions of years. This indicates that while Pluto's journey around the Sun may seem chaotic at first glance, there is a sort of order to it. Despite its seemingly erratic nature, predicting major events, especially involving chaotic orbits like Pluto's, presents significant challenges. The inherent unpredictability of these systems means long-term forecasts are often fraught with uncertainties. While mathematical simulations offer a solid way to understand and predict the behavior of celestial bodies, they also reveal the limitations in our predictive capabilities. These models heavily rely on the accuracy of initial conditions and the complexity of the interactions they simulate. Any slight error or simplification can lead to vastly different outcomes, making precise predictions a daunting task. Moreover, the turbulent nature of celestial orbits like Pluto reminds us of the constantly evolving and dynamic nature of the universe. While significant progress has been made in understanding space, Pluto's example serves as a reminder of how limited our knowledge of the universe still is. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can have far-reaching impacts, affecting the stability and paths of various bodies within the system. So why are major astrophysicists only now raising concerns about a potential collision between Pluto and Neptune? Despite these complex forces working to prevent such an event from occurring, Neil deGrasse Tyson, a prominent astrophysicist, provides a unique perspective on the mysteries of our solar system, particularly the fascinating case of Pluto. Tyson, well known for his role in reclassifying Pluto from a planet to a dwarf planet, offers thoughtful commentary on the evolving nature of celestial mechanics and the public's fascination with the unknown realms of space. His stance on Pluto's reclassification is rooted in the ever-expanding knowledge of our planetary system. He views this reclassification not as a downgrade, but as a necessary adjustment to our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and adaptation. He sees the complexities of orbits, such as Pluto's, as a sign of how much there is still to discover in space. The curiosity around these phenomena, especially the potential interactions between Pluto and Neptune, highlights the dynamic and unpredictable nature of our planetary system. His work emphasizes that the more we uncover about space, the more questions arise, driving us to explore further and refine our understanding of the universe. Michio Kaku, another renowned physicist and futurist, offers a different yet complementary perspective on the mysteries of space. Focusing on the often erratic forces that shape our universe, Kaku is known for his ability to connect complex scientific ideas with modern-day visions, making him a significant voice in discussions about celestial mechanics and the broader implications for humanity. Kaku's views on Pluto and its orbit underscore the need for continuous observation and advanced modeling to anticipate and understand potential cosmic events. He sees the interactions between celestial bodies as a crucial area of study, not only for academic curiosity but for practical implications. The potential collision between Pluto and Neptune, for example, is not merely a theoretical scenario but a reflection of the dynamic and often turbulent nature of space. Kaku's futurist perspective urges us to consider the broader implications of such events, from their impact on our understanding of the solar system to the potential need for future space interventions. His viewpoint highlights the importance of being prepared for the unexpected in space. Both Tyson and Kaku agree that space is a domain of endless discovery, and while our current understanding is significant, it is still limited. Their emphasis on the need for ongoing investigation and advanced modeling reflects the evolving nature of space science. They highlight the importance of not only understanding celestial mechanics as they exist now but also speculating on how they could change in the future. The potential collision scenario between Pluto and Neptune serves as a case study for the broader challenges and opportunities in space exploration. It emphasizes the need for robust scientific inquiry, advanced technology, and a readiness to adjust our understanding as new information emerges. For Tyson and Kaku, the mysteries of space, exemplified by Pluto's orbit, are a source of inspiration for the scientific community and humanity at large, encouraging us to continue pushing the boundaries of our knowledge. While there is a general consensus that, for years to come, Pluto and Neptune's orbits will remain stable due to their